I wanted to put a picture in this. Yeah, I have it. So I was a grad student at Georgia Tech in Atlanta, and somebody had taken the time to make this cone out of wood and actually have pieces that slide out of the cone, so they call conic sections. And I used to always look at that, like, that's really cool. I want to actually steal this. It's really neat. But the reason they call these different shapes conic sections is they're slicing through pieces of the cone. So for example, if you slice directly across the top and open it up, you're going to see a circle. If you slice sideways down the cone, you're going to see not a circle, but an egg. That's an ellipse. And if you slice this way down, you won't get the whole ellipse, you'll get part of it. And that's called a parabola, which actually I'm not going to cover in this class because you're going to see it over and over and over. Parabolas are like the only functions you really see after this. And then if you slice this way, you don't get exactly a parabola, you get something we call a hyperbola. And I remember seeing this stuff as a high school student and then maybe seeing it again as a college student. But you see it in one little section. And then I got to tell you, as a math professor or getting my PhD, I never saw it again, except when I had to teach it. So it wasn't my favorite thing, to be honest with you. But I learned to like it after some time because I saw its relevance. And I think that was what was missing. Now, the relevance that's in your book is about planets. So they talk about orbits of planets, having a circular, I mean, this is kind of really interesting now, but when I was younger, I didn't think it was that interesting, so maybe you don't think it's that interesting either. But if you have a planet and it orbits around a sun or star, having a circular orbit is a very good thing, the closer it is to being a circle. If you have an elliptical orbit, which I don't know if you're following the news, they're finding new planets all the time that may have potential life. Having a very elliptical orbit is a bad thing. You don't want that because you can imagine like your seasons would be all off kilter and you might get too close to the star at some point and too far away from the star. So you want to have actually a nice circular looking orbit. You also can have, if you have two elliptical orbits with two planets, they can crash into each other. And that's also an undesirable effect. So you want to calculate how close your ellipse, your oval, is to being a circle. So you can think of the oval as being a deformed circle. Like, oh, that's not a good orbit for a planet, so I wish it was. Ours is not perfectly a circle, but it's really, really close. The Earth going around the sun. So that's what the context you usually hear it, where when I was a kid, I was thinking, I don't care. But I guess it's more exciting for you today because back then when I was a kid, they didn't know that there was other planets out there, exoplanets from our solar system that may harbor life. So that's kind of cool. And the orbit thing actually is really important again. The application I'm going to show you is medical. These formulas to make these shapes, just like a parabola is y equals x squared, they all have formulas. And this is the formula for a circle centered at x0, y0 with radius r. And yes, you're writing it down. It is the blacklist. You're going to have to know this. So what do I want from you? I just want you to recognize that it's a circle. Recognition. So I don't want you to be able to like crank out formulas as circles and do all the other stuff. But the one thing I'd like you to retain from this class is when Dr. Forgeston looks at the class and says, what is this? That someone from my class will go, that's a circle. Don't the rest of you guys know that? That's what they look like. Ellipses differ from circles because they have denominators under the x jump and y jump, and these two denominators cannot be the same number. The a and the b are different. And conic sections are always set to be equal to 1. There's two types of ellipses. You could have an egg that's lying down on the ground, and that happens if the a is bigger than the b, or you could have an egg that's standing up, like the human body. I think I look like an egg. Right? So the egg that's standing up, the d is bigger than the egg. Hyperbolas this is the formula for hyperbola. What's different about it, it has a minus sign. So it's exactly like the ellipse, but it has a minus sign in the center. And they can look like this, which I haven't seen this too much. But there are people who I work with that see hyperbolas quite a bit. But you can also see a hyperbola that looks kind of like a parabola. It goes up like this. I copied and pasted. I copied and pasted the formulas right here for the hyperbola. You can also see a hyperbola that looks like this. I have seen this before when it comes to eating and activity. There was a researcher who went to India in the 1950s, and he looked at people's activity levels, and he also looked at how much food they ate. And in India, actually, in the 1950s, this is really probably possible because people tend to eat the same kinds of foods there. And what he found is people who were really, really active ate a lot. Not a surprise. The laborers, they ate a lot. But also, people who were really sedentary ate a lot too. So the graph that he formed was a hyperbola. So people who were sedentary were going up like this, the activity levels were on the y-axis, and the people who were really active were up like this. And there was actually a minimal point in the center somewhere where it was like moderately active people ate the least. And I'm always thinking, it's called the Maillard curve. It's really interesting. It's French. I always think about that. In fact, I want to run an experiment with mice to test that out. I don't know if you've ever seen someone who's been in an accident or seen them after. You'll see that they tend to gain a ton of weight. Yeah. And the idea is that they might be not changing their eating, but their activity couldn't possibly make up that differential. So they must be eating more. And so it would be the Maillard curve, that they're sedentary and eating like a Tour de France bike racer. So you've seen it. You've also seen it with ex-football players. Right? Ex-football players, you see that they gain a tremendous, Mary Lou Retton, not ex-football player, but ex-gymnast, gained a ton of weight. So when they became less active and more sedentary, their intake must have gone up. Mice, you can control mice. The ellipse? That's a good way to remember it, right? It has something to do with space, eclipse, ellipse. It's a good way to remember that. That's what it's related to. So the above list with the little cartoons, you don't have to be fancy. See how I drew the cartoons next to the side? Like just as a reference, egg that stands up looks like this, egg that lays down looks like this. That will be exactly the way I will ask this on the exam. So now you have a red list and a black list. You don't need a picture for a circle. Do you? No. You wait till you see my circles. You don't want my picture of a circle that looks like an ellipse.
Wait, what did you say was the other list?
This list that I just gave you, this list of formulas with all the little cartoon pictures.
So memorize the formulas?
Yeah, you do. It's not that hard once you start using it. You'll see. You just have to remember that the circle is the same as the ellipse, except that the A and the B are the same. The ellipse has a plus, the hyperbola has a minus. It's not that bad. Yeah, the circle is the same as the ellipse, except the A and the B are the same, right? They're not, you don't have a different letter. And the ellipse has a plus sign, and the hyperbola has a minus sign. They're easy to, like once you memorize it, they're easy to keep apart.
Wait, why is it, when you get to the other spot, right, it says y minus y, 0 to 0.
Right, so this one makes this picture, this one makes this picture.
Oh, can you go back to that?
You're recording this, right?
Yeah, it's all recorded. It's recorded.
Time.
So if the x comes first, it makes this picture. The y comes first, and we see the other picture.
They usually represent x0 as h and y0 as 1k something, right?
I don't know why they do that.
I saw that.
Yeah, I don't know why they do that, right? I need to know where my center is. I want that 1 point. Why wouldn't you call it x0, y0?
I saw that, that's why.
Yeah. You know, H and K have nothing to do. I mean, that seems to me strange, right?